All right. Now, this afternoon, the first speaker is Dr. Hagos. He is from Botswana International University of Science and Technology, Botswana. And the title of his talk is Solving Split Multiple Variational Inequality Problems in BANACH Space. So, Dr. Hagos, you can start your talk.
Thank you, Chair.
Welcome.
Good evening and good afternoon.
Thank you.
First, I would like to thank the organizers, Dr. Mahada and Dr. Adamayo, for organizing this special session to help us share our experiences with each other. And the title of my topic is Solving Split Multivariational Inequality Problems in BANACH Space. This is a joint work with Prof. Habtu Zagaye in the same university and same department here. Here are the outlines of the presentation. I'll just introduce the problem and discuss some of the literatures. And I'll highlight some definitions that are important in our study. And then I'll go to the main result and followed by numerical examples and conclusions. Okay, I will just start by defining one of the main problems in variational inequality. We just consider any non-empty subset of a real Banach space C. Then the multivariate variational inequality problem associated with a function f and c is defined by this one. Find x star, which is in C, and u star in f of x, so that this inequality one is satisfied. We call this problem multivariate variational problem because f of x is multivariate function. And there is another similar problem, we call it multivariate dual variational inequality problem, which is finding a point x star, which is in C, that satisfies inequality 2. And the two problems are two different problems. We can see this problem 2, the solution of problem 2 are always solutions of problem 1. Those multi-valued dual variational problems, the solution of this multivariate dual multivariational problem are subsets of the solutions of problem 1, which is multivariate variational inequality problem. And the two solutions are the same when f is continuous and pseudo-monotone. If f is continuous and pseudo-monotone, the two problems are the same. That means solution of problem 1 is the same as solution of problem 2. But if f is more than pseudo-monotone, like quasi-monotone, the two are not the same. That means solutions of 1 may not be solution of 2. But we know all solutions in 2 are solutions in 1. Because in 2, any solution x star works for all u in f of x. That's why all solutions of 2 are solutions of problem 1. And Broder was the first to introduce this problem 1, who was extended this variational inequality problem. This is the general one, problem 3. This is the general variational inequality problem, which is finding a vector u star in C such that this inequality 3 holds. We call this variational inequality problem. We call it the classical variational inequality problem. It was Broder who extended this problem to multivalued problem. And this multivalued is just an extension of this problem 3 and has been studied by several researchers. And this problem 1 is a very general problem, and it offers a unified method of studying wide range of problems like Nash problem, fixed point problem, and game theory for multivariate mappings. And there are several algorithms that are introduced to solve this problem one. And there is another more general class of this variation inequality problem 3. This problem 3 means a classical one. Just to add a split, we just add split one, the split variation inequality problem. They just added a map T such that the solution of 1, which is this one, and this solution of this one must satisfy a U star element of the fixed point of T. Now he added two maps A and T, where T is non-expressive mapping and A is just boundary linear map. And this problem was examined by Tian and Jiang in Hilbert space setting. And when you see this problem 4, this one is an extension of problem 3. If we put T to be identity mapping, that means we know every identity in identity map, every set is a fixed point because X is mapped to X. Therefore, every set is identity. It's a fixed point. That's why problem 4 would be equivalent to problem 3 if we take T to be identity mapping. And this Tian and Jiang, they used non-expansive mapping for T and A to be linear mapping, and F monotone and Lifshitz. And the algorithm they propose, it is weakly convergent to the solution. It's not strong convergent. And there are several studies, several methods used to solve this problem 4. And as this inertia method, it was discussed by Dr. Solomon and Dr. Mangustu. And this inertia method helps to accelerate the convergence of the scheme. And there are lots of studies using this inertial method to accelerate the convergence. Now our aim is to introduce a problem which is multi-valued split variation inequality problem, which generalizes 4 and this 4 is just a single value, but 1 is multi-valued. Therefore, we need to extend both those problems. We extend this one, problem 1, into multi-valued. And this one to, yes, this one. Now our aim here is to extend the problem by Tian and Jiang into, here is a considered Hilbert space. Therefore, we need to extend this one to Banach space. And instead of single value, we use multi-valued. Therefore, we are extending problem 4 and problem 1. Therefore, in problem 4, we are extending to real Banach space instead of Hilbert space. And instead of single value, we are extending it to multi-valued. And then from problem 1, we are just extending this one into split variation inequality problem. Then our aim is to develop an algorithm to solve this problem. Because if F and T are single valued, we are getting problem 4. If T is identity mapping, we are getting problem 1. So for this one, is a more general problem. And since we are going to extend into Banach spaces compared to Hilbert spaces, because this is a little more general. And we are planning to introduce inertia in this problem. If you can add that inertia, it will accelerate the convergence of the scheme. Okay, there are some definition. I will not go in detail. I will just state some of the important terms that we use. Just one of them is smooth space, and then strictly convex space. From this one, we can define what uniformly convex space is. And you can see the P uniformly convex space definitions for those ones. And uniformly smooth. And here are the examples: small LP, capital LP, and Sobolev space are examples of 2 uniformly smooth and P uniformly convex if P is between 2 and infinity. If P is in this interval, those 3 spaces are 2 uniformly smooth and P uniformly convex. If P is between 1 and 2, those spaces are 2 uniformly convex and P uniformly smooth. And we know if P is 2, then small LP, L2, and small L2 are Hilbert spaces. So for our aim is to use P, which is different from those values, for P different from 2. Because if we use P is equals to, we are in Hilbert space. And this one, we introduce the generalized duality mapping. We use this one to help us extend the work for Hilbert space into Banach spaces. And these are some definitions for pseudo-monotone and quasi-monotone for multivariate functions. And we introduce this Hausdorff metric defined on bounded and closed subsets of a set D. It's just maximum of the supremum of the distance between set and every element of that set, the other set. And if we need, we all know that's what's the definition of fixed point. And in the case of multivariate, if it is multivariate, we say that U star is a fixed point if U star is an element of E of U star. In the case of single variate, U star must be T of U star. But here, since T is multivariate, we need this to U star to be an element of T of U star. And here are some basic definition for quasi-Bregman non-expansive, because we use this Lyapunov distance and Hausdorff distance. And this Lyapunov distance is given by Alba, is defined by this formula. It's formula 8. So on the Lyapunov distance. And if the Hausdorff distance is less than or equal from distance, which we call it quasi-Bregman non-expansive. And if you find K, which is element of 0, 1, such that the Hausdorff is less than or equal to this 2, the sum of these two, we call this one quasi-Bregman strictly pseudo-contractive. But if K is 0, that means we call this one quasi-Bregman non-expansive, because if K is 0, they will be equivalent to equation 10. Equivalently, we can use 11, so 12, 12 years. I can't see those equations, that's why I think it's 11. 11 and 10 are equivalent. Okay, now to the main results. We have this conditions, C1 up to C8. That's why I define those uniformly convex and uniformly smooth, because we are focusing on real Banach spaces which are two uniformly convex and uniformly smooth. This one's for the Banach spaces, and T is just quasi-Bregman strictly pseudo-contractive mapping, which is number 2. And this others are also, you can just read it. And we define this algorithm. This is a algorithm we use to solve that problem. We just introduced, in this case, we use this double inertia because we are using three known values from the iteration xn minus 2, xn minus 1, and xn. If we use xn minus 1 and xn, we call it inertia. But if we are using three of them, we call it double inertia. And in this case, we have used double inertia. That means we are accelerating the algorithm, like we call it double acceleration. And then these are the 6 steps. You can just have a look on this number of steps. And then I will go to the main theorems. The first one is the boundedness. The sequence generated by the algorithm is bounded. And then after boundedness, we go to the convergence. If all conditions C1 out to C8 are satisfied with non-zero values of f of x, then the solution, the sequence generated by algorithm 3.1 converges to x star, which is in omega, meaning omega is this one. It's the solution of the multi-valued dual variational inequality problem, and ax is element of the fixed point of T. That means it converges to x star, which is element of omega, where this x star is the projection of u to omega. U is this one. Just we pick any. Okay, it's not here. It's u is any element of E. We can just pick any element. Then we project it to the solution set omega. Therefore, this x star is the projection of u to the solution set. That means the closest point to u from omega is the solution of the algorithm. That means this is a strong convergence theorem. The proof is big, that's why I didn't include the proof of the theorem. And here are some consequences of the results. If you assume f and t to be single valued, we are back to problem 4. And this algorithm works and is strongly convergent. And if we take an identity I for t is equals identity, now the problem will be changed to problem 1, which is only multi-valued variational inequality problem. And this the solution, the sequence that's generated by this algorithm converges to this solution set, where this x star is the projection of u to this solution set. And the last one is when we take u is equal to 0. If u is 0, that means the solution set will converge to a point x star with minimum norm. Because since it's converging to closer to u to 0 mean it's a number that a vector with minimum norm. And it converges strongly to this x star with minimum norm. These are some of the applications of the main result. And we can go to the numerical example. In this case, we just consider R4 for A1 and R2 for E2 with standard Euclidean norm. We defined Fx as this one. This is the inner product. Xa with this inner product mean it's like a dot product x dot A in R4. And this F is quasi-monotone. It's not pseudo-monotone. This function is not pseudo-monotone because if pseudo-monotone is equivalent to multi-variational inequality problem. That's why we consider only quasi-monotone, which is not pseudo-monotone. And we define T to be this one. It's a set valued. And we define the Hausdorff and we get this one, which means T is quasi-Bridgman strictly pseudo-contractive mapping. And we consider this A to be boundary linear operator. And this is a fixed point of T to 0. And this X star is a solution set in omega. And then the iteration with those initial values, it converges to this X star. And here are the simulations. I just zoomed in this one, two of them, three of them are the same figure, but I just took different interval to see the graph. As for different value of theta 0 mean it's without inertia. Theta 0.6 mean with larger inertia. As you see, when you increase the value of the theta, that means the solution converges to the solution set. All of them converge, but you can see as theta increases, it converges faster. You can see in this the second on the right hand side. The one below all those graphs is theta equal to 0.6. That means when we take theta larger means inertia, but with higher value. When it's 0 means no inertia. It's the solid line here. That means the algorithm with inertia converges faster than the algorithm without inertia.
You have 2 minutes.
Okay, thank you. And this one's for different value of mu. This one is for the line search. If we take mu to be larger, I think it's helping the algorithm to pick the accurate value. That's why as mu increases, we can see the line converge to, the error converge to 0 quickly. When you compare 0.2 and 0.001, there is a big difference. Okay, and this one is for small LP, for P between 1 and 2. That means when P is 2, it's Hilbert space. When P is between 1 and 2, it's a Banach space, but not Hilbert. That's why we have two values of P's, P4 over 3, which is between 1 and 2. You can see the solution converges to 0. The error converges to 0. That means Xn converges to X star, where our X star is the solution, which is this one. This is the solution set. Therefore, it converges to the solution set. And as you can see, when theta is 0 and theta is equal to 0.5, that means when theta is 0 means with no inertia and inertia. That means when there is inertia, it converges faster. You can see it in this figure. As this one for Hilbert, when P is 2, you can see the same thing, it converges, but when mu is larger, it converges faster. And here are just some of the conclusions from the study. We just developed this strongly convergent alternative method to solve the multi-valued split variational inequality problem in two uniformly convex and uniformly smooth real Banach space. And we provide numerical examples that validates the theoretical results. And this one generalized with from lot of studies that are studied in single value multivariational inequality problem, and from weak convergent to strong convergent, and from Hilbert space to Banach space settings. And this is our extension from those in the literature. I think this is the end of the presentation. Thank you for listening.